Let's get started with our second volcanoes lecture. Here we're going to go through two lists about types of volcanoes and then types of hazards. This is volcanoes number 2 in our textbook. This is in chapter 4. And to get started, we're going to get this list going. Types of volcanoes. Not all volcano edifices look the same or are the same because there's different degassing that occurs as bubbles escape or melt, and there's different compositions. They're going to produce different things. The main type of volcano that the normal person pictures is called a stratovolcano. We're going to get a sketch going here of a stratovolcano. We're going to draw something like Mount Rainier near the Seattle area, where here's like the top of Mount Rainier and the fairly steep sides at a certain angle, and it's a huge mountain that actually dwarfs the mountain ranges around it. The little city of Seattle sits down below it because, and we'll put the Space Needle in for those of you who know what Seattle looks like. This is a good picture for a stratovolcano. We have our vent up here at the top. You can have like satellite vents. We call parasite vents here on the sides. That's pretty common. They're called stratovolcanoes because the layers of the volcano are built up through time of ash falls and lava flows over hundreds of thousands to millions of years have created a strata, right? That means bed in its interior. All right, so let's get some of this written down, then I'll show you a picture. Oh, we should do a scale bar here. So how tall are they? They are like 1,000 meters to 5,000 meters tall. These are big, and their bases are very wide, on the order of maybe let's say 1 to 10 kilometers. These are big volcanoes. All right, so they are stratified with layers of ash and lava from different eruptions over their lifetime. How long is their lifetime? It's hundreds of thousands to millions of, well, let's say this. Let's go thousands to million years in order to build these things up. They are associated with subduction zones and the Ring of Fire. Famous examples of subduction zone, Ring of Fire volcanoes, well, Rainier, which I've drawn in the US in 1980, Mount St. Helens erupted. We could put that down. Other countries have them too. Mount Fuji is probably the most famous, and then Popocatépetl in Mexico is another great example. But that list could go on and on and on. The eruption style that dominates is Plinian. However, we can have essentially all other styles as well. Volcanian, Strombolian, and effusive eruptions of mafic and felsic lava. Should we write all that? We're going Plinian, Strombolian, Volcanian, effusive, mafic, and effusive felsic. All of those eruption styles are going to be associated with stratovolcanoes. The last thing to put down about a stratovolcano is its composition. They tend to be intermediate. However, you can have eruptions that are basaltic, and you can also have eruptions that are even rhyolitic. We'll throw in one of my favorite pictures, and then we'll move on. Here is Popo in the country of Mexico, creating that classic cone form, snow-capped eruption even happening. It's a tall mountain, a huge mountain, dominating a landscape. Shield volcanoes are the next type of volcano to get into. And a shield volcano is constructed from mafic lavas, almost entirely. And it's the building of layer upon layer of mafic lavas with low viscosity that creates the form that's so characteristic for the shield volcano, which is like a shield on its side, where here is, let's say, the island of Hawaii, here's the crater and the vent right here, but the slope is very gentle. Where you should put that, it's gentle slopes constructed from low viscosity lavas. Our great example of shield volcanoes are hotspots, but you can also have them at rifts And the Hawaiian Islands are a great example. So let's just say Hawaii. Their size can be humongous to smaller, so their size can be hundreds to thousands of meters tall, but that's very limited compared to their distal footprint, their footprint, which is in the 10 to hundreds of kilometers. They can be humongous. Olympus Mons on Mars is huge, but it doesn't look huge because of those gentle, shallow slopes. We'll get a picture in here and move to the next. Yeah, in fact, let's put this picture right underneath my sketch, and you can see how gentle the slope of this Hawaiian volcano actually is. It's huge. It actually gets snow capped sometimes at the top, but it's gentle-sided. All right, number 3, the third type of volcano. This might be the most common type of volcano on planet Earth, but they're little. And these are the cinder cones. And what a cinder is a mafic chunk of pumice. It tends to be small, like the size of a marble. And so if you can get an eruption that's making all these little mafic pumices produced from, here we go, mafic pumice produced from Strombolian eruptions, you can get a little volcanic edifice that built up over maybe 50 years. And so one of the things we should say about this is that these are short-lived, less than 50 years. Whereas our I didn't put that for shield volcano. Shield volcano could be on the order of thousands of years to millions of years to build them up. All right, but the cinder cone is short. It's like 50 years. And so it totally looks different. And what dominates a cinder cone is a really wide crater and kind of a short, stubby form. The height is on the order of 100 meters, and the base is something like a kilometer. So compared to us or a building, they're pretty big, but not compared to some of these other volcanoes. I'm going to put a speckled dot pattern on this because that's our cinder, and those cinders blast out from Strombolian eruptions and land on the sides. Sometimes these are associated with little breakouts where some of the magma will crack. The lava will crack out the side of the base of the volcano and produce a lava. This is what cinder cones look like. So we got mafic, good. Strombolian, good. Breakout lavas, they are associated with any tectonic environment. Let's get a picture in. This is a picture of a cinder cone from Arizona. It doesn't even have a name. That's like how common these things are. And I want you just to see how big that crater top is relative to the height of the volcano itself. They're relatively small. You could climb that in 30 minutes. The fourth type of volcanic edifice is called a caldera. And what's different about a caldera is that it is not a positive edifice, it is a destructive one. It is a hole in the ground. Destructive. It's a negative topography. And the thing that produces that destructive edifice is collapse. So let's say destructive edifice from collapse as crater floor, from collapse of crater floor as magma chamber empties. These are big. These are big features. We could have something that looks kind of like a graben actually, but you'd want to picture this as circular. And there's a magma chamber down here, but it emptied, and that emptying weakened the area above it, and so this block fell down, and it's this hole in the ground that is the caldera itself. And you can imagine ash actually shooting out from along these faults on the margins of the caldera. These tend to be associated with our biggest Plinian eruptions, which evacuate the most magma. They are felsic in composition most of the time, because Plinian and felsic go together, and the scale of these is big, and so they are measured on kilometers. They're measured on kilometers in terms of distance, and also measured in kilometers cubed in terms of volume. These can be found in most tectonic environments. The most famous examples of calderas maybe is Yellowstone. The big eruptions that have occurred at Yellowstone have produced calderas. Crater Lake in Oregon is beautiful. And what it is a single lake sitting within the downdrop block of a caldera. You could imagine Crater Lake used to be a volcano whose sides continued up at this slope. But 7,000 years ago, an eruption occurred that blew all this material away, leaving for us now this hole in the ground that's filled with water. All right, that's a caldera. Now, to finish off volcanoes, what we should talk about is what are the hazards? What are the things that can cause death, suffering, destruction, both to humans and to economy? And we'll do this as a list. I'll put in pictures here to show these, and of course you can read about this in your textbook, and you can read about this on Wikipedia. You can watch videos about these things. Ashfall is our first volcanic hazard, and the hazard of ashfall is buries infrastructure, roads, roofs, and the thing is, like, it's buries infrastructure. It doesn't melt like snow, and it's not light like snow, and so it can cause collapse if it builds too much. The kind of picture you might be able to have for this is, let's say we have a volcano, and here's our eruption column, and then here's our umbrella region blowing downwind, and if our infrastructure of a city was here, this material is raining down on top of our city and can eventually bury it. Picture please, Professor. This is a good example from the Canary Islands, where this was probably a beautiful house, got buried as ash blew out of this volcano back here and has buried the landscape, burying the house, which would not be fit to live in, and certainly also burying the trees. Our next hazard that we'll get into is lavas. I'll throw the picture in right here. Lavas can produce two main types of hazard, and it's going to depend on their composition. So let's go, here we go. Number 2 are lavas. And I've put in a picture of a mafic lava. And the threat of mafic lava is very limited. It will bury infrastructure or cause fires. That's about it. Fires or bury infrastructure. Right? Like, let's say it just kind of goes across a road. That's the kind of thing it does. Look at these tourists in Iceland. They're standing right on the edge of it because the lava itself is moving pretty slow, and they can run away if they need to. And so it's this tourist destination. Now, lavas that are felsic can present much more of a trouble because felsic lava builds up these really steep sides, and those steep sides of that lava could collapse. Steep sides collapse. And if they collapse, it's an avalanche, and avalanches are sudden, fast, and dangerous. Did I put one of these in? I did not put a picture of this in. So what I'll do is I'll snag a picture from last lecture as a repeat, and you can visualize how if this side of this gets over-steepened, it could then collapse into an avalanche, and someone hiking down here would be not a clever individual. That would be a very dangerous place to be because of the potential collapse of the sides of the felsic lava. When this avalanche of a collapse occurs, it's called a pyroclastic flow. It's going to be number 3. The definition for pyroclastic flow can be found in the name. Pyro is fire, clastic is broken, and so these are avalanches of hot ash and gas. Avalanche of hot gas and ash. They form in 2 different ways. They form either one from collapse of felsic lava dome, That's an easy way to produce an avalanche. The second way is from collapse of Plinian eruption column. So if we have our volcano and it is erupting up, and here's our umbrella region, this part of the material right here could not be able to rise any further and actually will collapse down the side of a volcano into an avalanche that then could travel very far. We should put a star under pyroclastic flows because these are a major killer of people. They can be devastating because they are sudden, fast, and travel far. Like hundreds of miles an hour fast. And travel far, like multiple kilometers, miles and miles distance. And so you think you're far enough away, but the pyroclastic flow just keeps coming, and eventually gets to where you were standing. Here's an example from the Caribbean of a small stratovolcano that when it last erupted, it had its eruption column rising up like so. And parts of that eruption column collapsed down the sides in directions A's, B's, and C's to produce these deposits, which are the pyroclastic flow deposits. And if there was a city here, it is now buried. A lahar is a very similar, I'm going to put in a picture here of a lahar, we'll define it next. A lahar is also a mass wasting event, and it is a mud flow. So in this case, we have the mud flow coming out of the vent of Mount St. Helens and burying the landscape. And this mud is produced by hot ash falling on snow, producing this natural disaster. All right, so let's go ahead and get that in our notes, and we're almost done. Lahar, defined as, that's number 4, I believe. Lahar is defined as a volcanic mud flow. And we're going to say usually produced by melting the snow cap of a volcano. These are also major killers, and volcano agencies, geological surveys have put in many safety systems in order to prevent people who live in valleys near volcanoes from not knowing these are coming, because they are fast and they can travel far. Many volcanoes today are monitored for lahars, and that's because in the 1980s there was a really significant disaster in Colombia that woke people up to the dangers of lahars. And our final, there are other hazards, but our final hazard to go through today in an introductory class is volcanic gas. And a volcanic gas can be poisonous for us to breathe. And so if we do not see or know that poisonous gas is being emitted from a volcano, we could cause ourselves to suffocate. We can't see it. These are limited in its destructive and hurt to humanity, but it happens pretty regularly because let's say a snowboarder or a skier doesn't know that some volcano has started to emit some poisonous gases on its side, and they hit a pocket and then die. To show you an example of volcanic gas steaming out of the side of a volcano, I'll leave you with this picture, and we can see and imagine how gas is emanating from these fissures. Let's try these fissures here. And these would be dangerous to approach without a gas mask.